Hello Chem 1B, this is chapter 18, lecture video 4, and we're going to begin by discussing the second law of thermodynamics, which is about the change in entropy of the universe. And universe is kind of a funny word here. When we mean this, we mean the system plus surroundings, which is pretty much everything in existence, i.e. the universe. So how do we calculate this? We take delta S of our system and we add it to delta S of our surroundings. Now, this allows us to determine whether a process is going to be spontaneous or not. It's the first way we're going to learn how to do that. There are actually 4 total ways of determining whether a reaction is spontaneous or not. And the first is using delta S universe. If it is greater than 0, that is a spontaneous process. So if we can calculate it and determine whether it's positive or negative, that'll tell us whether our process is spontaneous or not. Now, how do we do this? Well, the first is we need to calculate delta S, which is just products minus reactants, right? Delta S naught of our reaction is equal to the sum of the S naught values of the products minus the sum of the S naught values of the reactants. And if we just do that subtraction, that gets us delta S of our reaction, i.e. the system, because generally the reaction is our system. So we can use Hess's law for entropies to do this. Now, if we want to do this for delta S of the surroundings, the next question is, okay, well, how do we calculate the energy dispersal component, i.e. the delta S of our surroundings? Well, do we use Hess's law for entropies? Well, no, we don't. That's not going to work. So we need to talk about how we can do that. So how do we calculate delta S of surroundings? Because it's the energy dispersal component, it's way more related to delta H of our system. And so we have this equation here, delta S of our surroundings is equal to negative delta H of our system divided by T. Now this T has to be in Kelvin. And there's some other small issues that we'll talk about as we go through this. Why? Well, energy dispersal is really, delta H is just equal to Q, which is our energy transferred under constant pressure. So energy being dispersed here is important. Now, why is this negative? That's kind of important. Well, this is the system, and we want the surroundings. And we know system and surroundings are always going to be opposite sign. So this, if we plug back into our previous equation, gives that delta S of the universe is equal to delta S of our system minus delta H of the system divided by T. Again, delta S of the universe is greater than 0 if it's a spontaneous process. Now, when we do problems like this, like for this problem, let's go back. We already calculated this value on lecture video 1 for chapter 17. And I'm just trying to say, hey, great. You guys know how to calculate delta H of a reaction, and if you don't, come talk to me via office hours or email. That's something you learned how to do in Chem 1A. You needed to have looked up the delta H naughts of formation here to get this guy, but this is what you'll get if you solve this equation for delta H. Now I need to take this and plug into here to get delta S of my surroundings. Now, some of you might have already noticed there is going to be a problem in the future because this value here is in kilojoules, and this value up here for our system of delta S naught is in joules. And we can't use kilojoules and joules in the same equation. They have to be in the same units. Either you got to change our delta S of our system to kilojoules, or you got to change our delta H of our system / reaction to joules at some point. So we got to plug that in. I'm changing that right here, right? That's what the thousand's coming from, is me changing from kilojoules to joules. We're going to assume that we're at 25 degrees Celsius. That's a generally good assumption. So if you're not told temperature at any point in any problem in this chapter, or the next one for that matter, you should just assume 25 degrees Celsius. And 25 degrees Celsius is this, right? I'm just changing from Celsius to Kelvin here, which is that value there. And we divide this all out, we get 1917 joules per Kelvin. And that's our energy dispersal component. Now, we already talked about this. This reaction is definitely spontaneous. It was one of my examples I used to describe spontaneity. So let's look at what our delta S of the universe ends up being when we do this, right? So we have our system, matter dispersal. We have the surroundings, that's our energy dispersal. To get delta S of the universe, we have to add these two values together. And when you add them, you get this value, which is positive. Which means this is a spontaneous process. Now, there's another thing that we need to talk about here. Earlier, I kind of hinted at the fact that, well, not hinted, I straight up told you that product-favored reactions are spontaneous. This means there is a second way to determine whether a reaction is spontaneous. Now, we haven't gotten away from equilibrium 100%. Remember that a reaction that is product favored has an equilibrium constant that's greater than 1. So this is another way to determine spontaneity. So now at this point you now know two ways to figure out whether a reaction is spontaneous. If your equilibrium constant is greater than 1, spontaneous process. If delta S of your universe is greater than 1, is positive, spontaneous. Both of those two would tell us that the process is spontaneous. Now at the end of chapter 18, so not this chapter but the next chapter, you will know 4 different ways to determine whether a reaction is spontaneous or not. And these are the first 2. We're going to learn about the third one in just a second. Okay, let's finish this video off with a problem. And so we're going to calculate delta S universe at negative 34 degrees Celsius for this reaction here, using our table here and the delta H given in the problem. Now, as we know, delta S universe is equal to the delta S of our reaction plus the delta S of the surroundings. Now we can calculate delta S of our reaction just using our S0 values given here in this table and the reaction itself, right? So if we want to calculate that, delta S of our reaction is equal products minus reactants, right? So let's do the products first. So Fe plus CO2 is our products, right? So what's Fe's value? It's 27.3, and there's only one of it. This reaction is balanced, so we're just going to go, okay, cool. Add that to CO2, which is 213.8, and subtract our reactants, which is FeO, 60.75, plus 197.7. And we can just hit equals here on our calculator. Negative 17.4 joules moles Kelvin is what we get here. Now we need to calculate delta S of our surroundings. Now, as we learned earlier, delta S of our surroundings is equal to negative delta H of our reaction over T. Well, we have delta H of the reaction and we have T, so we can solve this, right? So I have negative 1 basically times 34.6 kilojoules per mole, all over our temperature. Now we need to calculate the temperature in Kelvin, and we have it in Celsius. So first we need to calculate that. And if you don't know how to do that, just let me know. But I'm not going to show that work here. You should get at around 239.2 Kelvin here. And if we just divide these out, right, 34.6 divided by 239.2 times -1 gets us -0.1446 kilojoules per mole Kelvin. Now, this is in kilojoules. We need to make sure these two units are in the same energy units. So I'm going to multiply by 1,000 joules per 1 kilojoule here and get that it's negative 144.6. The last step here is just to add these two to each other, right? We just got to plug them into our original equation, right? So delta S of my universe, in this case, I'm just going to kind of abbreviate there, is going to be equal to negative 17.4 plus negative 144.6, and that's going to give me, give or take, negative 162 joules moles Kelvin. So here's my answer, and because it's negative, we know this reaction is not spontaneous. And that's it. So if you have any questions, as always, please email me or come to our Zoom meeting discussion sessions.